You were taught that particles do not have positions until you look at them. You were taught that the universe is fundamentally random, that nothing is determined until measurement forces reality to pick a lane. You were taught that quantum mechanics proved this, that the experiments demanded it, that there was simply no other way to read the data. And here is the part that should disturb you. None of that was ever true. There has been a fully deterministic, fully observer-independent interpretation of quantum mechanics that reproduces every single prediction of the standard theory. It was first proposed in 1927. It was independently revived in 1952. It has never been disproven. It has never been shown to conflict with a single experiment. It makes exactly the same predictions as the quantum mechanics you were taught in school, except it does it without wave function collapse, without observer dependence, without any of the paradoxes that have haunted the field for a century. Particles have positions. They always have positions. They move along definite trajectories guided by a real physical wave. And the reason you have never heard of this theory, the reason it appears in almost no textbooks, the reason generations of physicists were trained as if it did not exist, has nothing to do with science. It has to do with what happened in a conference room in Brussels in October of 1927, and what happened to a young physicist in America 25 years later. And what happens to anyone in any field who stands up and says the emperor has no clothes at the wrong time, in the wrong room, to the wrong people. The theory is called pilot wave theory, and if it is correct, then the universe is not random. It never was, and everything that has happened since the Big Bang, including this moment, including you deciding to watch this video, was written into the initial conditions. That is where this is going. But first, you need to understand how this started, because the story of how a correct theory gets erased from a scientific discipline for 60 years is itself one of the most unsettling things you will ever hear about how knowledge actually works. October 1927, Brussels, the 5th Solvay International Conference on Electrons and Photons. If you have seen the famous photograph, the one that gets called the most intelligent picture ever taken, this is the event. 29 physicists in the frame. 17 of them were or would become Nobel laureates. Front row, left to right, you have got Langmuir, Planck, Curie, Lorentz, Einstein, Langevin, Guy, Wilson. Richardson, middle row includes Debye, Knudsen, Bragg, Kramers, Dirac, Compton, de Broglie, Bohm, Bohr. Back row, Picard, Henriette, Ehrenfest, Hertzen, de Donde, Schrödinger, Verschaffelt, Pauli, Heisenberg, Fowler, Brillouin. That is the room. And in that room, over 5 days the future of physics was decided. Not by experiment, not by mathematics, by social pressure. The youngest person in that photograph who mattered for this story was Louis de Broglie. He was 35 years old, a French duke, the 7th in the de Broglie line, born into one of the most aristocratic families in France. His older brother, Maurice, was an experimental physicist who had attended the first Solvay conference in 1911 and brought home stories that captivated the younger sibling. Louis originally studied history at the Sorbonne, intending a career in diplomacy. Then he read Poincaré. He lost 6 years to World War I, working on wireless communications at the Eiffel Tower. When he came back to physics after the war, he produced what might be the most consequential doctoral thesis in the history of science. In 1924, de Broglie submitted a thesis titled Recherches sur la théorie of quanta, Research on the Theory of Quanta. The proposal was so radical that his examining committee did not know what to make of it. Paul Langevin sent a copy to Einstein, who reportedly said the thesis deserved a Nobel Prize, not a doctorate. What de Broglie had proposed was that every moving particle carries an associated wave. Every single one, not just photons, electrons, protons, everything. The wavelength of that wave equals Planck's constant divided by the particle's momentum. Lambda equals h over p. It was confirmed experimentally by Davison and Germer in 1927, and de Broglie got the Nobel Prize in 1929. But de Broglie wanted more than a formula. He wanted to understand what the wave physically was. By the time of the Solvay conference, he had developed what he called his theory of the double solution, which later became known as pilot wave theory. The proposal was elegant. Particles are real objects, they have positions at all times, they move along definite trajectories, but their trajectories are guided by a real physical wave. The particle surfs on the wave. That is the pilot wave. The wave evolves according to the Schrödinger equation, and the particle follows the wave's guidance. Think about what that means for the double slit experiment, the one that supposedly proves particles do not have positions. In the standard telling, a particle approaches two slits, somehow passes through both slits simultaneously while it is not being observed, and interferes with itself on the other side. Nobody can tell you how that works, because the standard interpretation says you are not allowed to ask. In pilot wave theory, the answer is straightforward. The wave passes through both slits. The particle passes through one. The wave interferes with itself on the other side of the barrier, creating a pattern of peaks and troughs in the velocity field. The particle, guided by that velocity field, gets steered into the interference bands. Each individual particle goes through one slit. The wave goes through both. The interference pattern builds up over many particles because the wave shapes every trajectory. There is no mystery. There is no paradox. There is a particle and there is a wave, and they do different things. De Broglie presented this at Solvay, and Wolfgang Pauli stood up and destroyed it. Or at least, that is the version you would have gotten for the next 70 years. What actually happened is more complicated and more damning. Pauli raised a technical objection about inelastic scattering, specifically about whether de Broglie's framework could handle a technique Enrico Fermi had been using. The objection sounded devastating in the room. De Broglie, quiet and formal by temperament, aristocratic in a way that did not lend itself to intellectual combat, offered a rebuttal that was actually correct. But the room did not hear it that way. The definitive scholarly analysis, published in 2009 by Guido Bacialupi and Anthony Valentini at Cambridge University Press, Quantum Theory at the Crossroads, went back to the original conference proceedings and showed that de Broglie's response was valid and Pauli's objection was not fatal. The theory could handle inelastic scattering. It was not missing anything essential. But in that room, it did not matter. What mattered was who had the social authority and who did not. Max Born and Werner Heisenberg stood up at that same conference and declared, "This is a direct statement from the proceedings. We consider quantum mechanics to be a closed theory whose fundamental physical and mathematical assumptions are no longer susceptible of any modification. A closed theory, not open for discussion, not subject to alternatives, closed." Heisenberg later recalled with satisfaction that their group, Bohr, Ehrenfest, Pauli, himself, felt that the game was now won. The game, that is the word he used. De Broglie went home and quietly gave up on his own theory. He became a follower of the Copenhagen interpretation, the framework championed by Niels Bohr, which said that the wave function does not describe a physical wave. It describes your knowledge of the system. When you measure something, the wave function collapses and the system randomly picks one outcome from the available options. There is no reality beneath the measurement. There are no trajectories. There are no positions until you look. Asking what the particle is doing when you are not observing it is not just unanswerable. It is meaningless. De Broglie accepted all of this for 25 years, and he might have gone to his grave a convert, except that in 1952, a physicist he had never met, writing from political exile in Brazil, published 2 papers that blew the whole question open again. Papers that proved de Broglie had been right all along, that Pauli's objection was answerable, that every single alleged impossibility proof against hidden variable theories was wrong, and that the Copenhagen interpretation was not the only way to make sense of quantum mechanics. It was a choice, a deliberate philosophical choice that had been dressed up as scientific necessity. That physicist was David Bohm, and what happened to him is one of the worst things the physics establishment has ever done. David Bohm was born on December 20th, 1917 in Wilkes-Barre, Pennsylvania, coal mining country. His father Samuel was a Hungarian Jewish immigrant who ran a furniture store. His mother Frida suffered from mental illness that the family never discussed. Bohm was awkward, solitary, the kind of kid who wandered into the woods alone while his classmates played together. He discovered science fiction at age 10 through a magazine called Amazing Stories, and something in him shifted permanently. He studied physics at Penn State, then moved to Berkeley for his doctorate under J. Robert Oppenheimer. Oppenheimer was brilliant, charismatic, and politically connected in ways that would turn toxic. Bohm's thesis work on plasma scattering was immediately classified for the Manhattan Project. And then the Kafkaesque part. Bohm was denied the security clearance he would have needed to read his own research. He could not defend his thesis in the normal way. He could not write it up properly because the material was classified and he was not cleared. Oppenheimer had to personally certify that the work was worthy of the degree. At Princeton, starting in 1947, Bohm found himself working near Albert Einstein, who lived nearby at the Institute for Advanced Study. Einstein took an interest in Bohm, called him his spiritual son. They talked frequently, sometimes for hours, walking the streets of Princeton or sitting in Einstein's office at Fuld Hall. Einstein was the most famous physicist alive and also the most prominent critic of the Copenhagen interpretation. He did not believe quantum mechanics was complete. He believed it was a statistical approximation of some deeper reality, the way thermodynamics is a statistical approximation of molecular mechanics. His 1935 paper with Boris Podolsky and Nathan Rosen, the EPR paper, had laid out the most devastating critique of Copenhagen. Either quantum mechanics is incomplete, meaning there are real properties that the theory fails to describe, or reality is non-local, meaning measurements in one place instantaneously affect distant systems. EPR argued that both options were unacceptable. Copenhagen's defenders chose to deny incompleteness and accept that quantum mechanics was complete as it stood. The argument had been raging for 16 years by the time Bohm arrived at Princeton, and Einstein was losing. In 1951, Bohm published a textbook called Quantum Theory. It was so clear and so thorough that Einstein himself praised it, and then immediately challenged Bohm on it. "If you can explain the standard theory this well," Einstein said after reading it, "then look at what it actually implies. Look at the assumptions. Look at von Neumann's impossibility proof. See if there really is no way around it." This is the extraordinary thing about Einstein's role in this story. He was the catalyst. He was the reason Bohm looked. He was the intellectual father of the search that produced the 1952 papers. And then, when Bohm found the answer, Einstein rejected it. Not because the answer was wrong, because it was not the kind of answer Einstein wanted. He wanted a local hidden variable theory. Bohm gave him a non-local one, and Einstein could not accept non-locality. He called it spooky action at a distance, and spent his remaining years searching for a local alternative that Bell would later prove does not exist. John von Neumann was one of the greatest mathematicians of the 20th century. In 1932, he had published a proof that appeared to show, with mathematical rigor, that no hidden variable theory could reproduce the predictions of quantum mechanics. It was in his book Mathematische Grundlagen der Quantenmechanik. For decades, this proof was cited as the final word. If you wanted to argue for a deterministic quantum theory, von Neumann had already proved you wrong. Case closed. Get back to work. Bohm read the proof carefully, and he found his way through it. Not by finding a technical flaw, at least not at first. He just built the theory and showed it worked. On January 15, 1952, Physical Review published 2 papers by Bohm, a suggested interpretation of the quantum theory in terms of hidden variables, parts 1 and 2, volume 85, number 2, pages 166 through 193. These papers went far beyond what de Broglie had proposed in 1927. Bohm addressed every objection Pauli had raised. He incorporated a complete theory of measurement. He extended the framework to many particle systems. He introduced a new concept, the quantum potential, a field that guides particles but does not diminish with distance the way classical forces do. And he proved mathematically that his theory reproduced every single prediction of standard quantum mechanics. Not approximately, exactly. Every interference pattern, every energy level, every scattering cross-section, all of it. He also showed why von Neumann's impossibility proof did not apply. Von Neumann had made an assumption about how the results of measurements must combine. An assumption that seemed innocuous but was actually a very specific restriction that no hidden variable theory was required to satisfy. The assumption was that the expected value of a sum of observables must equal the sum of the expected values, even for observables that cannot be measured simultaneously. That is true for quantum states. It is not required to be true for the underlying hidden variables. It was a subtle error, but it invalidated the entire proof. Here is the thing that should make you angry. Bohm was not the first person to find this error. A German mathematician and philosopher named Greta Hermann had identified the flaw in 1935. 3 years after von Neumann published, she wrote a paper pointing it out. Nobody noticed. The paper was published in a philosophy journal, not a physics journal, and the physics community ignored it. For more than 50 years, generations of physics students were taught that von Neumann had proved hidden variables impossible and that proof had been known to be wrong since before World War II. John Bell, who independently discovered the same flaw in 1966, was characteristically blunt about it. He said the proof was not merely false but foolish. Think about what that means. For decades, the primary justification for dismissing any alternative to Copenhagen was a mathematical proof that was not merely false but foolish, and the man who said so was the most careful and rigorous thinker in quantum foundations in the 20th century. But Bohm never got the chance to change physics from inside the profession, because by the time his papers appeared, the United States government had already destroyed his career. In 1942, as a graduate student at Berkeley, Bohm had joined the Communist Party. He stayed for about 9 months and quit, later saying the meetings were petty and exhausting, and that they discussed nothing of significance. It was a decision made by a 24-year-old in the middle of a world war where the Soviet Union was an American ally, and it was a decision that would follow him for the rest of his life. In May of 1949, Bohm was subpoenaed by the House Un-American Activities Committee to testify about Oppenheimer's political associations. He invoked the Fifth Amendment. He refused to name names. On December 4, 1950, he was arrested and indicted for contempt of Congress. Princeton suspended him immediately. He was forbidden to set foot on campus. The physics department had recommended his reappointment just 1 month earlier. Princeton's president, Harold Dodds, wrote that Bohm had not indicated that he possesses those qualities of personality and judgment which should be expected of a member of its faculty. Not that he was a bad physicist, that he had bad personality and judgment for refusing to inform on his colleagues. Bohm was acquitted on May 31st, 1951. It did not matter. Princeton let his contract expire. Einstein tried to hire Bohm as his research assistant at the Institute for Advanced Study, but the director of the institute, J. Robert Oppenheimer, Bohm's own doctoral advisor, the man who had classified Bohm's thesis and then told security services that Bohm was politically suspect and possibly dangerous, blocked the appointment. Oppenheimer told Bohm to leave the country. In October 1951, Bohm left for Brazil, taking a position at the University of São Paulo. 1 month after he arrived, American officials at the consulate confiscated his passport and returned it stamped as valid only for return to the United States. He was trapped. He could not attend international conferences, he could not visit Einstein, he could not participate in the global physics community. He was a political prisoner in exile, publishing the most important papers in quantum foundations in a generation. And the people who should have been engaging with that work were either unable to reach him or unwilling to try. Brazil was not easy for Bohm. He spoke little Portuguese when he arrived. The physics department at São Paulo, while well funded by Brazilian standards, was not a hub of quantum foundations. The climate disagreed with him. He suffered from depression, a condition that had troubled him intermittently since adolescence, and that the isolation of exile worsened considerably. In letters to friends, he described feeling cut off from the intellectual community that had sustained him. He took Brazilian citizenship in 1954, partly as a practical measure and partly because returning to the United States felt impossible. When he tried to travel to conferences in Europe, the Brazilian government, under pressure from American officials, initially refused to issue him a new passport. He was stateless in every sense that mattered, and yet it was during this period of maximum isolation that Bohm produced his most revolutionary work. The 1952 papers were largely finished before he left Princeton, but he refined them in São Paulo, working through the mathematical details with an intensity that his correspondence reveals as almost obsessive. Later, reflecting on the experience, Bohm told the physicist F. David Peat something remarkable. He said, "It liberated me. I was able to think more easily and more freely." Cut off from the professional pressures that shape what questions physicists are allowed to ask, Bohm asked the question nobody else would touch. And he answered it. He moved to Israel in 1955, taking a position at the Technion in Haifa, then to the University of Bristol in 1957, where he began his long collaboration with a young South African physicist named Yakir Aharonov. Together they discovered the Aharonov-Bohm effect, published in Physical Review in 1959, which showed that an electron can be affected by an electromagnetic potential even in a region where the electromagnetic field is zero. This was experimentally confirmed and remains one of the most striking results in quantum mechanics. It earned Aharonov considerable recognition. Bohm, characteristically, received less. In 1961, Bohm moved to Birkbeck College, University of London, where he would spend the rest of his career. It was at Birkbeck that he met Basil Hiley, and the two began a collaboration that would last 31 years, until Bohm's death. Birkbeck was not a prestigious institution by the standards of Cambridge or Oxford. It was a college for working adults, founded in 1823 as the London Mechanics Institution. But it gave Bohm something he had not had since Princeton: intellectual freedom, a collaborator who shared his convictions, and enough distance from the mainstream of American and continental physics to work without interference. It was during this exile that the physics establishment made its decision about Bohm's theory, and the decision was not to disprove it, the decision was to ignore it. Oppenheimer organized a seminar at Princeton, while Bohm was in Brazil, specifically to find errors in the 1952 papers. Physicists went through the mathematics line by line. They spent hours. They found nothing wrong. And Oppenheimer's response, as reported by multiple sources, was this: if we cannot disprove Bohm, then we must agree to ignore him. He also called the work juvenile deviationism, a phrase borrowed from Stalinist political vocabulary, applied, with no sense of irony, to a man who had been driven out of his country for alleged communist sympathies. Heisenberg dismissed the theory as a superfluous ideological superstructure. Pauli, who had opposed de Broglie's version at Solvay, wrote to colleagues calling Bohm's work nearly plagiarism. But in a private letter directly to Bohm, Pauli conceded something extraordinary. He wrote that he could no longer see any longer the possibility of any logical contradiction as long as your results agree completely with those of the usual wave mechanics. Read that again. Pauli admitted the theory worked. Then he dismissed it as artificial metaphysics. Not wrong. Metaphysics. A philosophical objection dressed as a scientific one. Bohr reportedly called Bohm very foolish. Leon Rosenfeld, Bohr's closest assistant and a committed Marxist who saw opposing Bohm's causal interpretation as somehow ideologically necessary, was openly hostile. And Einstein, the man who had inspired Bohm's search in the first place, was paradoxically unimpressed. In a letter to Max Born on May 12, 1952, Einstein wrote, "Have you noticed that Bohm believes, as de Broglie did by the way 25 years ago, that he is able to interpret the quantum theory in deterministic terms? That way seems too cheap to me." Einstein's objection was not to determinism. He wanted determinism. His lifelong insistence that God does not play dice was a demand for determinism. His objection was to the wave function living in configuration space rather than physical space. It did not smell like something real to him. He wanted a theory where the physical reality lived in three-dimensional space, where things could be pictured, where locality was preserved. Bohm gave him determinism at the cost of non-locality, and Einstein could not accept the trade. He died 3 years later, on April 18, 1955, still searching for a local theory. Bell proved 11 years after Einstein's death that no such theory exists. The local realism Einstein spent his final years defending is mathematically impossible. The universe chose non-locality. Einstein just did not live long enough to see the proof. So every major figure in physics had a reason to dismiss the theory. And none of those reasons were that it was mathematically wrong. None of those reasons were that it conflicted with experiment. Oppenheimer could not find an error. Pauli admitted it worked. Einstein thought it was inelegant. Heisenberg called it ideology. Bohr called it foolish. And that was it. A mathematically valid, experimentally indistinguishable interpretation of quantum mechanics was placed in a drawer, and the drawer was locked. Not for a year, not for a decade, for 60 years. And here is where the story gets worse, because it was not just Bohm who was silenced. It was the entire question. The phrase "shut up and calculate" has become shorthand for the culture that dominated physics for most of the 20th century. The phrase was coined by Cornell physicist N. David Mermin in his April 1989 column in Physics Today. It is frequently attributed to Richard Feynman, which tells you something about how deeply the attitude was embedded. The attribution to Feynman is false, Mermin has said so publicly, but it persists because it feels true. Feynman was the most celebrated physicist of his generation, and his disdain for philosophical questions about quantum mechanics was legendary. When students asked him what quantum mechanics meant, he would say, "Nobody understands quantum mechanics." It was not a confession of ignorance, it was a command. Stop asking. The question is above your pay grade. Above everyone's pay grade. Do the calculation, get the number, move on. Mermin described his own experience as a graduate student at Harvard in the late 1950s. His advisors warned him, "You will never get a PhD if you allow yourself to be distracted by such frivolities." The frivolity they were referring to was asking what quantum mechanics means. This was Harvard, the top physics department in the country, and the official position was that asking the most basic question about the most fundamental theory in physics was a frivolity, a distraction, a career-ending mistake. The mechanism of suppression was not a conspiracy. It was something more effective. It was a professional norm, enforced not by a central authority, but by thousands of individual decisions made by grant reviewers, tenure committees, journal editors, and thesis advisors, all of whom had been trained in the same culture, and all of whom understood, without needing to be told, that foundations work was not real physics. The norm was self-perpetuating. Students who asked foundational questions were redirected toward productive research. Those who persisted were marginalized. Those who succeeded in mainstream physics internalized the norm and passed it to their own students. The result was a discipline that could calculate the magnetic moment of the electron to 12 decimal places and could not tell you what an electron is. Max Tegmark, now at MIT, organized one of the first informal polls on quantum interpretations at a conference in 1997. He found that even among physicists actively interested in foundations, there was no consensus. But the poll itself was treated as a novelty, as entertainment, not as evidence of a serious professional problem. The idea that the foundational questions of quantum mechanics were unresolved was treated as a fun fact, not an emergency. This was not about one physicist being marginalized. This was about an entire area of inquiry being declared professionally toxic. If you wanted to ask what measurement actually means, what the wave function physically is, whether particles have positions, whether there are alternatives to Copenhagen, you were not just wrong. You were unserious. You were unprofessional, and if you persisted, you would not get grants, you would not get published. John Clauser learned this the hard way. Clauser, who would eventually win the 2022 Nobel Prize for experimentally testing Bell's inequalities, was told by his Columbia faculty in the 1960s that testing quantum foundations was going to destroy my career. When he approached Richard Feynman to discuss the possibility that quantum mechanics might not give correct predictions for entangled particles, Feynman threw him out of his office. Clauser's funding applications to the National Science Foundation were rejected. He later said the reviews did not argue about the physics. Their theme was that NSF should not waste money on fruitless pursuits. Clauser stated plainly, "I thought it was important at the time, even though I was going to ruin my career by doing it. And in some sense, I did. I have never been a professor." The man who won the Nobel Prize for experimentally confirming one of the most important theorems in physics was never a professor, because the community decided that testing fundamental physics was unprofessional. And then there was John Bell. Bell was born on July 28, 1928, in Belfast, working class, a family where neither parent nor any sibling had finished high school. His mother sewed his academic gown from blackout curtains left over from the Second World War because they could not afford to buy one. He attended Belfast Technical High School because grammar schools were beyond the family's means. He spent a year working as a laboratory technician at Queen's University Belfast before professors noticed his ability and allowed him to attend lectures. He earned first-class honours in experimental physics in 1948 and a second degree in mathematical physics in 1949, both from Queen's University Belfast, institutions a world away from the elite physics departments of Cambridge, Copenhagen, and Princeton, where the foundations of quantum mechanics had been shaped. Bell spent his career at CERN as a particle physics theorist and accelerator designer. Quantum foundations was not his job. It was, in his own words, a hobby pursued in evenings and on holidays. He and his wife Mary, also a physicist, had both given up tenured positions at Harwell to take untenured posts at CERN. That is how seriously they took their work. But the foundations work, the work that would make Bell the most important figure in quantum physics since the founding generation, was something he did in his spare time, because doing it professionally would have been career suicide. Bell had been troubled by quantum mechanics since he was a student. He found comfort only in learning that Einstein shared his doubts. Then he read Max Born's textbook, Natural Philosophy of Cause and Chance, published in 1949, which cited von Neumann's impossibility proof against hidden variables. Bell recalled, "Having read this, I relegated the question to the back of my mind and got on with more practical things. The proof seemed definitive. Hidden variables were mathematically impossible. End of story. Move on. Build accelerators. Calculate cross-sections. Stop thinking about what it all means." Then came 1952. Bell read Bohm's papers, and the impossible had been done. Bell's own words are worth sitting with for a moment. "In 1952, I saw the impossible done. It was in papers by David Bohm. Bohm showed explicitly how parameters could indeed be introduced into non-relativistic wave mechanics, with the help of which the indeterministic description could be transformed into a deterministic one. More importantly, in my opinion, the subjectivity of the orthodox version, the necessary reference to the observer, could be eliminated." Bell's fury was barely contained, but why then had Bohm not told me of this pilot wave, if only to point out what was wrong with it? Why did von Neumann not consider it? More extraordinarily, why did people go on producing impossibility proofs after 1952 and as recently as 1978? That last detail is critical. People were still publishing proofs that hidden variable theories were impossible 26 years after Bohm had built one that worked. This is the pattern you need to understand. Von Neumann publishes a flawed proof in 1932. Hermann finds the flaw in 1935. Nobody notices. Bohm builds a working hidden variable theory in 1952. Explicitly demonstrating that the impossibility claims are wrong. The physics establishment ignores it. Bell independently finds von Neumann's error in 1966 and publishes a paper pointing it out. People continue citing von Neumann as definitive. New impossibility proofs are published as late as 1978. This is not science. This is institutional inertia, armed with social pressure and enforced by career incentives. Bell's frustration with the orthodox position was deep and philosophical. He wrote in 1981, making a virtue of necessity, and influenced by positivistic and instrumentalist philosophies, many came to hold not only that it is difficult to find a coherent picture, but that it is wrong to look for one, if not actually immoral, then certainly unprofessional. Immoral. Unprofessional. Those are the words the physics community used for people who wanted to understand what their own theory meant. Bell was describing a culture in which the most basic scientific question, what is actually happening, had been declared out of bounds. Not because the question was unanswerable, and Bell knew exactly what the answer looked like, because Bohm had shown him. In pilot wave theory, particles have definite positions. They move along definite trajectories. The wave function is a real physical field that guides those trajectories. And the measurement problem, the deepest unsolved puzzle in quantum foundations, simply vanishes. In the standard theory, you have two contradictory rules. Rule 1 says the wave function evolves smoothly according to the Schrödinger equation when nobody is looking. Rule 2 says the wave function suddenly collapses to a random outcome when somebody measures it. There is no definition of what counts as a measurement. There is no mechanism for the collapse. There is no explanation for why Rule 1 turns into Rule 2. This is the measurement problem, and it has been the central embarrassment of quantum mechanics for almost 100 years. Pilot wave theory does not have a measurement problem. There is only one rule. The wave function always evolves via the Schrödinger equation. It never collapses. Particles always have positions, so measurement devices always have definite states. Pointers always point. Cats are always alive or dead, never both. The appearance of collapse emerges naturally through a process called decoherence, where different branches of the wave function stop overlapping in configuration space, and only the branch containing the actual particle positions has any further effect. Bohm described this mechanism in 1952, decades before decoherence became fashionable in mainstream physics. He solved the measurement problem before most physicists had even properly articulated it. Bell saw this clearly and advocated for it with increasing openness as his career progressed. In his 1982 essay on the impossible pilot wave, published in Foundations of Physics, he wrote what may be the most important paragraph in the philosophy of quantum mechanics. While the founding fathers agonized over the question particle or wave, de Broglie in 1925 proposed the obvious answer: particle and wave. Is it not clear from the smallness of the scintillation on the screen that we have to do with a particle? And is it not clear from the diffraction and interference patterns that the motion of the particle is directed by a wave? Particle and wave, both real, both doing their respective jobs. No paradox, no mystery, just physics. And then Bell asked the question that nobody wanted to answer. Why is the pilot wave picture ignored in textbooks? Should it not be taught, not as the only way, but as an antidote to the prevailing complacency? To show that vagueness, subjectivity, and indeterminism are not forced on us by experimental facts, but by deliberate theoretical choice. That last sentence is the single most important statement in this entire story. Vagueness, subjectivity, and indeterminism are not forced on us by experimental facts. They are a choice. Everything you were taught about quantum mechanics being inherently weird, inherently random, inherently unknowable, was not discovered. It was decided by a group of physicists in the 1920s and 30s who chose a particular philosophical framework and then, over the following decades, made it socially impossible to choose differently. Bell also noted the extraordinary double standard in how Bohm's work was received. Why were people so intolerant of de Broglie's gropings and of Bohm? For 25 years, people were saying that hidden variable theories were impossible. After Bohm did it, some of the same people said that now it was trivial. They did a fantastic somersault. First, it was impossible. Then, when someone did it, it was trivial. The one thing it could never be was important. But Bell did more than advocate for pilot wave theory. He noticed something about it that would lead to the most important theorem in quantum physics. Something that changed everything, and something that makes the suppression of pilot wave theory even more inexcusable. Because what Bell noticed, tucked inside the mathematics of Bohm's guiding equation, was an explicit causal mechanism whereby the disposition of one piece of apparatus affects the results obtained with a distant piece. The guiding equation for any particle depends on the positions of all other particles in the system, not the nearby particles. All of them, everywhere, instantaneously. This is non-locality, and it is the key to everything that comes next. Because Bell asked himself a question that nobody had thought to ask before. He asked whether non-locality was just a feature of Bohm's particular theory, or whether it was a feature of any theory that reproduces the predictions of quantum mechanics. And what he proved, in a 6-page paper published in 1964, was that it is a feature of any theory. Every hidden variable theory that reproduces quantum predictions must be non-local. This is Bell's theorem, and it means that the universe does not respect locality, the principle that things can only be directly influenced by their immediate surroundings. Something deeper is going on, something that connects distant parts of the universe in a way that classical physics says should be impossible. Bell published this result in a journal called Physics Physique Physica, Volume 1, Number 3, pages 195 through 200. It was an obscure journal. It folded shortly afterward. The paper received no direct response for more than 4 years. Think about that. a paper proving that the universe must be non-local, that no local theory can reproduce the predictions of quantum mechanics, that the debate between Einstein and Bohr had a definitive mathematical resolution, sat in the literature for 4 years without a single published response. It was not refuted, it was not criticized, it was not discussed. It was ignored. The same treatment Bohm's papers had received. The same silence. The pattern was not accidental. It was structural. The first person to write to Bell about it was John Clauser in 1969. Clauser was a graduate student at Columbia who had stumbled across Bell's paper while looking for something else. He read it and immediately understood its significance. He wrote to Bell. Bell wrote back, and Clauser began the experimental program that would eventually, 53 years later, win him the Nobel Prize. But in 1969, Clauser was a student proposing to test whether the most successful theory in physics was actually correct. His advisors told him he was insane, the same Clauser who would be told his career was over for wanting to test it. Bell knew what it meant that his work was rooted in Bohm's. He knew his theorem was a direct consequence of taking pilot wave theory seriously enough to examine its structure. The non-locality was there in Bohm's equations, obvious if you looked. Bell looked, and what he found is that non-locality is not a quirk of pilot wave theory. It is a feature of reality. The physics community spent decades trying to avoid this conclusion. They failed. Alain Aspec's experiments in 1982 violated Bell's inequalities by 5 standard deviations. The loophole-free tests in 2015 closed every remaining escape route. And in 2022, the Nobel Committee gave the prize to Aspect, Clauser, and Anton Zeilinger for experimental work on Bell inequalities. The Nobel Prize in 2002 was a vindication of Bell's theoretical framework. But Bell never saw it. On October 1st, 1990, at the age of 62, John Stuart Bell suffered a cerebral hemorrhage in Geneva and died. He was still on the CERN staff. He was widely expected to win the Nobel Prize. The award cannot be given posthumously. And here is the detail about Bell's death that you need to understand in the context of this story. Bell spent his career doing foundations work as a hobby, in evenings, on holidays, because the profession he worked in had decided that asking what quantum mechanics means was unprofessional. The greatest theorem in quantum physics came from a man who had to do the work in secret, on his own time, because the culture of physics would not let him do it openly, and he died 12 years before the Nobel Committee acknowledged that the work mattered. Bohm died 2 years after Bell. On the evening of October 27th, 1992, David Bohm called his wife Sarah from his office at Birkbeck College, University of London. His last words to her were, "You know, it is tantalizing. I feel I am on the edge of something." An hour later, his taxi pulled up at home and Bohm suffered a massive heart attack. He was 74 years old. He had spent the last 40 years of his life in exile, first physically, then intellectually. He never returned to the United States as a citizen until 1986, when a lawsuit finally restored the citizenship that had been stripped from him 32 years earlier. De Broglie outlived them both. He died on March 19, 1987, at the age of 94. But here is the part of de Broglie's story that almost nobody tells. When Bohm published his papers in 1952, de Broglie read them and recognized immediately that Bohm had answered every objection that had driven him to abandon his own theory in 1927. Pauli's scattering problem was solved. The many-body extension worked. The measurement problem was resolved. De Broglie returned to pilot wave theory and spent the last 3 decades of his life working on it. The man who had been pressured into giving up a correct theory at the age of 35 came back to it at the age of 60 after a quarter century of following an interpretation he never fully believed in. Think about that for a moment. 25 years of a physicist's life, the prime years of his career, spent following a framework he was pressured into accepting at a conference in Brussels, when the theory he abandoned was correct the whole time. Now ask yourself why you have never heard this story. Ask yourself why the textbook you read in university or the popular science video you watched last year presented the Copenhagen interpretation as if it were the only option, as if particles not having positions were a fact rather than a philosophical choice, as if the randomness of quantum mechanics were discovered in nature rather than decided in a conference room. The answer is that the story was buried, not by a conspiracy, by something worse, by a professional culture that made it socially impossible to tell, and it is still being buried right now, not with the crude tools of McCarthyism or conference room intimidation, but with something more insidious: silence, textbook silence, the kind of silence where a theory that solves the central problem of your field simply does not appear in the chapter on interpretations, or if it does, it gets 2 paragraphs and a dismissal that reads like it was written by someone who never bothered to read Bohm's actual papers. Pick up any standard quantum mechanics textbook published between 1960 and 2010. Griffiths, Sakurai, Cohen-Tanuji, Shankar. Look in the index for Bohm or pilot wave or de Broglie Bohm. In most cases, you will find nothing. In a few, you will find a footnote. In almost none will you find a serious treatment. Griffiths, to his credit, includes a brief section in Introduction to Quantum Mechanics, but frames it as a curiosity. Sakurai's Modern Quantum Mechanics, used in graduate courses worldwide, does not mention pilot wave theory at all. Cohen-Tanuji's 2-volume Quantum Mechanics, over 1,500 pages of exhaustive treatment of nearly every aspect of the subject, does not discuss it. Landau and Lifshitz's 3-volume sequence on quantum mechanics, the Bible of Soviet and post-Soviet physics education, does not discuss it. Dirac's Principles of Quantum Mechanics, the founding text of the field, does not discuss it. The student comes away from any of these books thinking that the Copenhagen interpretation is quantum mechanics itself, not one interpretation among several. Meanwhile, the Copenhagen interpretation is taught as if it is quantum mechanics itself, not one interpretation of the formalism. Students learn that the wave function is a probability amplitude. That measurement causes collapse. That particles do not have positions between measurements. They learn this not as one framework says, but as this is what the math means. The distinction between formalism and interpretation is never drawn clearly, and the result is that generations of physicists leave graduate school believing that quantum indeterminacy is a fact about nature rather than a feature of one particular philosophical framework. They do not know there is an alternative. They do not know there has been an alternative since 1952. And they do not know that the alternative solves the measurement problem, eliminates the paradoxes, and reproduces every prediction of the theory they just spent years learning. A 2025 survey published in Nature, polling over 1,100 researchers working in quantum physics, found the following. 36% identified with the Copenhagen interpretation, 15% chose many worlds, 7% chose de Broglie-Bohm pilot wave theory. And here is the number that matters most. Only 24% of respondents said they were confident in their own choice. 3/4 of working quantum physicists are not confident in their own interpretation of the theory they use every day. That is not a field that has settled its foundational questions. That is a field that agreed to stop asking them. Compare that 7% for pilot wave theory to what you would expect if the theory were taught properly. If every graduate student learned that there exists a deterministic, observer-independent formulation of quantum mechanics that solves the measurement problem and reproduces all standard predictions, and that its suppression was driven by social and political factors rather than scientific ones. Do you think 7% is the number you would get? That 7% represents the physicists who went looking for alternatives on their own time, found Bohm's papers or Bell's advocacy, and decided the evidence was compelling despite their training telling them to look away. 7% is not the size of the theory's support, it is the size of the resistance. But something has been changing, slowly, grudgingly, with the kind of institutional reluctance that characterizes every paradigm shift in the history of science. Pilot wave theory has been clawing its way back, and the thing that accelerated its return was not a mathematical proof or a philosophical argument. It was something you could see with your eyes. Something so simple and so visual that it cut through decades of abstraction and made the pilot wave concept undeniable, not as a quantum theory, as a physical phenomenon. In 2005, two physicists at the University of Paris Diderot, Yves Coudert and Emmanuel Fort, were studying the behavior of small droplets of silicone oil bouncing on a vibrating bath. The setup was almost comically simple. You take a shallow dish of silicone oil, you mount it on a speaker or a vibrating platform. You tune the vibration frequency to just below the Faraday threshold, the point where the surface would spontaneously form standing waves. At that critical frequency, the surface is alive with energy, but not quite breaking into pattern. And if you drop a tiny droplet of the same oil onto that surface, something extraordinary happens. The droplet does not sink into the bath. It does not merge. It bounces each time it hits the surface. It creates a small circular wave, a ripple spreading outward at about 20 centimeters per second. And that wave is still spreading outward when the droplet lands again. Roughly 20 milliseconds later, the droplet lands on the wave it created on the previous bounce, and that wave kicks it forward. But not just the wave from the previous bounce. The bath retains a memory of previous bounces. Earlier waves are still present, still propagating their patterns superposed with newer ones. The droplet is walking on a wave field that encodes its own history. With each bounce, the wave field becomes richer, more complex, more informed by the path the droplet has already taken. The droplet begins to walk across the surface, propelled by its own wave field, steered by the interference of its accumulated wave history. The physics of why this works is specific and worth understanding. The vibrating bath is tuned to just below the Faraday instability threshold. At the Faraday threshold, the entire surface would spontaneously break into a standing wave pattern. Just below it, the surface is poised on the edge of instability. It is ready to oscillate, but needs a trigger. The bouncing droplet provides that trigger locally. Each impact excites a localized Faraday wave that persists for a time determined by how close the bath is to the threshold. The closer you tune to the threshold, the longer each wave persists. The longer each wave persists, the more previous bounces contribute to the current wave field. Physicists call this the memory parameter. At low memory, the droplet feels only its most recent bounce and walks in a straight line. At high memory, it feels dozens or hundreds of previous bounces, and its behavior becomes rich, complex, and startlingly quantum-like. Coudert and Fort called this a walking droplet, and what they observed over the following years was so striking that it sent a shockwave through the foundations of physics community, because the walking droplet was doing things that were supposed to be quantum. In 2006, Coudert and Fort published a paper in Physical Review Letters, Volume 97, Article 154.101. They had built a version of the single slit and double slit experiment for walking droplets. The droplet approached a barrier with one or two openings, and on the other side, over many trials, the droplets built up a pattern, an interference pattern, the same type of banded distribution that is supposed to be the hallmark of quantum behavior, the signature that supposedly proves particles do not have positions. And here it was, produced by a classical oil droplet that very obviously had a position at all times, walking along a definite trajectory, guided by its own wave. The parallel to de Broglie's pilot wave was immediate and unmistakable. Here was a particle, the droplet, with a definite position. Here was a wave, the surface wave created by the bouncing, that guided the particle's trajectory. The particle went through one slit, the wave went through both. The interference pattern emerged from the wave shaping the particle's path. This was pilot wave dynamics made visible on a tabletop. The walking droplet experiments did not stop at the double slit. In 2009, Eddy, Fort, Moisey and Kuda published results showing quantum tunneling analogues. A walking droplet approaching a barrier would sometimes cross it and sometimes bounce back, with probabilities that depended on the barrier's properties, mimicking the probabilistic nature of quantum tunneling despite the system being entirely classical and deterministic. In 2010, Fort, Proto, Boudou, Kuda, and their team published in the Proceedings of the National Academy of Sciences, Volume 107, pages 17, 5, 15 and following, showing that walking droplets confined to a circular corral developed quantized orbits. The droplets did not orbit at arbitrary distances, they settled into discrete orbital levels, determined by the wave field geometry. Quantized orbits in a classical system, the kind of thing that was supposed to require quantum mechanics. John W. M. Bush, a professor of applied mathematics at MIT, saw the Kuda-Fort results and recognized their significance immediately. Bush launched a systematic research program to catalog every quantum analog the walking droplet system could produce. His group, along with collaborators worldwide, spent the next 15 years pushing the system further and further. They found analogues of spin, of orbital angular momentum quantization, of Zeeman splitting in the presence of a rotating bath that plays the role of a magnetic field. They found statistics that, in certain regimes, resembled the Bohm rule probability distributions that are the bread and butter of quantum mechanics. Let me be honest about something here, because the walking droplet story is complicated, and the audience for this video is too smart to accept a simplified version. The original 2006 double slit result has been challenged. In 2015, 3 separate research groups attempted to replicate the original Kuda-Fort double slit experiment, and found that the interference-like pattern did not appear in their setups. The original experiment used only 75 individual trajectories, symmetrized to 150 data points, which critics argued was too small a sample and too easily biased. The walking droplet community took this seriously. It was a genuine experimental dispute, not a dismissal. But the story did not end there. In 2018, Giuseppe Pucci and colleagues from the Bush group at MIT published results showing diffraction patterns, not identical to quantum interference, but structurally analogous, in what they called the high memory regime, where the vibrating bath retains a long history of the droplet's previous bounces. The wave field in this regime is richer and more complex, and the droplet's behavior becomes more wave-like. And in 2022, Bush's group published a paper titled Real Surreal Trajectories in Physical Review A, Volume 106, Article L010203. The title is a reference to a famous thought experiment proposed by Englert, Scully, Sussman, and Walther in 1992, who had argued that Bohmian trajectories in certain interferometer setups would be surreal, meaning they would follow paths that seemed to contradict common sense. Bush's team showed that walking droplets in an analogous setup followed precisely the trajectories predicted by Bohmian mechanics, and that these trajectories, far from being surreal, made perfect physical sense when you could actually see the wave field guiding the particle. Then in 2025, Darrow and Bush published a proof in Foundations of Physics, Volume 55, Article 13, that formally connected de Broglie's original 1927 pilot wave proposal to Bohm's 1952 formulation, showing them to be mathematically equivalent in a way that had not been rigorously demonstrated before. Almost a century after de Broglie presented his theory at Solvay, the mathematical bridge between his intuition and Bohm's fully developed framework was finally completed. Now here is what you need to understand about the walking droplet experiments and what they do and do not prove. They do not prove that quantum mechanics is secretly a pilot wave theory. The walking droplet is a classical system. It obeys Newtonian mechanics. The oil bath is not a quantum wave function. There is a crucial difference that limits the analogy. In the walking droplet system, the droplet creates the wave and the wave guides the droplet. There is back reaction. The particle shapes the wave and the wave shapes the particle. In standard Bohmian mechanics, the wave function guides the particle, but the particle does not affect the wave function. The influence goes one way. More importantly, the walking droplet system has not reproduced entanglement. It has not violated Bell's inequalities. It cannot because it is a local classical system, and Bell proved that any system reproducing quantum correlations must be non-local. The droplet system is local. It lives in three-dimensional physical space. Quantum mechanics lives in configuration space, a space with 3 dimensions for every particle in the universe. That is a fundamental difference, and no tabletop experiment with oil droplets can bridge it. So what do the walking droplets actually prove? They prove something that might be more important than a direct quantum analog. They prove that pilot wave dynamics work. They prove that a system consisting of a particle with a definite position, guided by a wave that encodes information about the environment, can produce quantized states, interference patterns, tunneling behavior, and statistical distributions that look eerily like the predictions of quantum mechanics. They prove that the conceptual architecture of pilot wave theory is not a mathematical trick. It is a physical mechanism. You can watch it happen. And they prove something else, something that goes to the heart of the 60-year suppression. For decades, the standard dismissal of pilot wave theory was that it was metaphysical, that it added hidden variables to quantum mechanics for philosophical reasons, but made no new predictions and offered no new physics. It was just Copenhagen with extra baggage. This was the line from Pauli, from Heisenberg, from Bohr's school. The walking droplets demolished that argument, because here was a pilot wave system that was not metaphysical at all. It was right there. You could film it. You could measure the wave. You could track the particle. You could see the guiding equation at work. The objection that pilot wave dynamics are unphysical or metaphysical is not tenable when you can watch them happen in a dish of silicone oil in a laboratory in Paris. Bush himself has been careful and measured about the implications. He does not claim the walking droplet is a quantum system. He claims it is a proof of concept, a demonstration that the pilot wave framework produces quantum-like behavior in a system that is fully accessible to observation. In his 2016 Annual Review of Fluid Mechanics article, he wrote that the walking droplet system represents the first macroscopic realization of a pilot wave system, and argued that its quantum-like features warrant a critical revisitation of the potential shortcomings of existing models for quantum dynamics. A critical revisitation. That is polite academic language for you should go back and look at what you dismissed, because the evidence suggests you were wrong to dismiss it. But the physics establishment has been slow to revisit. The walking droplet results have generated excitement in foundation circles, in fluid mechanics, in applied mathematics. They have not generated a revolution in how quantum mechanics is taught. The textbooks have not been rewritten, the curricula have not changed. Copenhagen is still the default. Shut up and calculate is still the professional norm in most departments. And the 7% of physicists who identify as Bohmian are still, in most institutional settings, a fringe. That would be disturbing enough on its own. A valid theory, suppressed for decades, demonstrated in a physical system, and still marginalized. But here is where the story takes a turn, that makes the suppression look like the least important part, because everything up to this point has been about whether pilot wave theory is a legitimate alternative to standard quantum mechanics. The history, the politics, the walking droplets, all of that is about whether the theory works. And the answer is yes, it works. It always worked. It was never wrong. But the question that matters, the question that should keep you awake, is not whether it works. It is what it says. Because what pilot wave theory actually tells you about the nature of reality is far more unsettling than the fact that it was suppressed. The suppression is a scandal. What the theory implies is something else entirely. And to understand what pilot wave theory says, you have to go past the version you just heard. Past particles have positions, and waves guide them. Past the history and the politics, and the walking droplets. You have to go into the mathematics, not the notation, not the formalism in the way a textbook would present it, but what the equations physically mean when you stop treating them as abstract tools and start treating them as descriptions of reality. Because the equations say something that most physicists who dismiss pilot wave theory have either not fully absorbed or have chosen not to think about. And once you see it, you cannot unsee it. In standard quantum mechanics, the wave function is a mathematical object. It lives in an abstract space. You use it to calculate probabilities. When you measure something, the wave function collapses, somehow, and gives you an outcome. What the wave function is, physically, is a question the Copenhagen interpretation says you are not allowed to ask. It is a tool. Use it, get results. Do not ask what it means. In Bohmian mechanics, the wave function is real. It is a physical field. It exists in the same way that an electromagnetic field exists. It has a value at every point in its domain, and that value changes over time according to a precise equation, the Schrödinger equation. The difference, the thing that makes Bohmian mechanics strange in a way that even many physicists do not fully appreciate, is where the wave function lives. An electromagnetic field lives in three-dimensional space. It has a value at every point in the room you are sitting in. You can measure it here or there, or anywhere. It is a field on physical space. The wave function of a single particle also lives in three-dimensional space. It has a value at every point. So far, so normal. But the wave function of two particles does not live in three-dimensional space. It lives in six-dimensional space. 3 dimensions for the first particle, 3 for the second. The wave function of 3 particles lives in 9-dimensional space. The wave function of n particles lives in 3 n-dimensional space. This space is called configuration space, and it is not a mathematical convenience. In Bohmian mechanics, it is where the wave function physically exists. Now scale that up. The observable universe contains somewhere in the vicinity of 10 to the 80 particles. The wave function of the universe, the object that Bohmian mechanics says is physically real, lives in a space with 3 times 10 to the 80 dimensions. That is not a number you can visualize. It is not a space you can picture. It is a mathematical structure so vast that every metaphor for vastness you have ever encountered is pathetically inadequate to describe it. And that structure is, according to pilot wave theory, the arena in which the physical wave guiding every particle in the universe actually exists. This is where most people, including most physicists, get off the bus. The wave function living in configuration space feels too abstract, too remote from physical intuition, too far from the three-dimensional world we experience. Einstein felt this way. It was his primary objection to Bohm's theory. He wrote to Max Born that the theory did not smell like something real because the wave function did not live in physical space. And that instinct is understandable, but it is also, if you think about it carefully, a strange place to draw the line. Because the many worlds interpretation, which commands 15% support in that 2025 Nature survey, also has a universal wave function that lives in configuration space. The only difference is that many worlds says there are no particles at all, just the wave function. Just that single object in 3 × 10⁸ dimensional space, branching endlessly, with each branch containing an entire copy of the universe. In many worlds, you are not a collection of particles being guided by a wave. You are a pattern in the wave, a smear across configuration space, an abstraction of an abstraction. Pilot wave theory at least gives you particles, real objects in 3-dimensional space with definite positions. A world you can recognize. It just says that those particles are being guided by something that lives in a space you cannot see. And the thing doing the guiding, the wave function, does not care about distance. This is where Bohm's quantum potential comes in, and this is where the theory becomes genuinely disturbing. In his 1952 papers, Bohm showed that you can rewrite the guiding equation in a form that looks like classical mechanics. You get Newton's second law, F equals ma, with all the usual classical forces, plus one additional term. He called it the quantum potential and denoted it Q. The quantum potential is derived from the wave function. It depends on the shape of the wave function, on its curvature, on the way it bends through configuration space. And it has a property that nothing else in physics has. It does not diminish with distance. Every force you have ever encountered weakens as you move away from its source. Gravity falls off as 1/r². Electromagnetism falls off as 1/r². The strong nuclear force, despite being the most powerful force we know of, has a range of roughly 1 femtometer, about the diameter of a proton. Everything in classical physics obeys a simple principle. Far away things matter less than nearby things. The universe is, in the language of physics, local. What happens here depends mostly on what is here, and only weakly on what is far away. The quantum potential violates this principle completely. An electron at the edge of the observable universe contributes to the quantum potential acting on an electron in your brain with the same mathematical weight as an electron 1 angstrom away from it. Not approximately the same. Exactly the same. The quantum potential depends on the form of the wave function, not on its amplitude. Bohm described this using an analogy. Think of a ship at sea being guided by a radio signal. The energy to move the ship comes from the ship's own engines. The radio signal provides the information, the form of the motion. And a radio signal does not need to be strong to carry accurate information. A whisper can carry the same navigational instructions as a shout. The quantum potential is like the signal. It does not push the particle with force proportional to its amplitude. It informs the particle, shapes its trajectory, and it does so regardless of distance. Bell saw this and recognized it for what it was. In his 1987 paper, Are There Quantum Jumps?, he wrote explicitly about the non-local character of Bohm's theory. He pointed out that the guiding equation for any single particle in a many-particle system depends on the instantaneous positions of all the other particles. Not after a delay, not at the speed of light, instantaneously. He called it an explicit causal mechanism whereby the disposition of one piece of apparatus affects the results obtained with a distant piece. He was describing, in precise language, a universe in which everything is connected to everything else with no respect for spatial separation. And then Bell proved something that elevated this from a feature of one theory to a fact about nature. Bell's theorem, published in that obscure journal in 1964, is often described in simplified terms. People say it proves that quantum mechanics is weird, or that entanglement is real, or that Einstein was wrong about local hidden variables. All of that is true, but it misses the weight of what Bell actually demonstrated. What Bell proved is this. Take any theory that satisfies two conditions. First, the theory is local, meaning the result of a measurement at one location does not depend on what measurement is performed at a distant location. Second, The theory assigns definite values to measurable quantities prior to measurement, which physicists call realism. Bell showed that any theory satisfying both locality and realism must obey a set of statistical inequalities. These are Bell's inequalities, and then he showed that quantum mechanics predicts violations of those inequalities. In other words, if the predictions of quantum mechanics are correct, then locality and realism cannot both be true. At least one of them must go, and the experiments say quantum mechanics is correct. Alain Aspect's landmark experiments in Paris in 1982 measured correlations between entangled photons separated by 12 meters. He found violations of Bell's inequalities by 5 standard deviations. But Aspect's experiments had loopholes. The measurement settings were not chosen quickly enough to rule out the possibility that information traveling at the speed of light could have coordinated the results. It took another 3 decades to close those loopholes. In 2015, 3 independent experiments achieved what physicists call loophole-free Bell tests. Ronald Hansen's group at Delft University in the Netherlands, using entangled nitrogen vacancy centers in diamonds separated by 1.3 kilometers, published a violation of Bell's inequality with a p-value of 0.039. The Vienna group under Anton Zeilinger, using entangled photons, published similar results. And the NIST group in Boulder, Colorado, using entangled photons with high-efficiency detectors, closed the detection loophole. All 3 confirmed the same thing. Bell's inequalities are violated. Locality and realism cannot both survive. Think about what the Delft experiment actually demonstrated physically. 2 diamonds, each containing a single nitrogen atom substituting for a carbon atom in the crystal lattice, creating what physicists call a nitrogen vacancy center. Each nitrogen vacancy center can be entangled with a photon it emits. Those photons are sent through fiber optic cables to a station midway between the 2 diamonds, 1.3 kilometers apart, where they are subjected to a joint measurement that entangles the 2 distant nitrogen vacancy centers with each other. The 2 diamonds are then measured with measurement settings chosen by random number generators quickly enough that no signal traveling at the speed of light could communicate the setting choice from one lab to the other before both measurements are completed. And the correlations between the results violate Bell's inequality. The universe does not obey the rules of any local theory. Hansen's group had to run the experiment for weeks to accumulate enough data. The event-ready scheme, where successful entanglement is heralded by a joint photon measurement at the midpoint, succeeds roughly once per hour. Out of 245 total heralded events, the Bell inequality was violated with a p-value of 0.039. Subsequent runs with more data have pushed the significance higher. Combined with the Vienna and NIST results, which closed different loopholes using different physical systems, the case is beyond serious dispute. Every escape route that clever theorists spent 50 years constructing, every loophole, every potential classical explanation, has been sealed shut. The physics community awarded the 22 Nobel Prize to Aspect, Clauser, and Zeilinger for these experimental achievements. But the Nobel citation was carefully worded. It praised the experiments for establishing the violation of Bell inequalities and pioneering quantum information science. It did not say what the violations mean, because saying what they mean requires choosing an interpretation, and the profession has spent a century avoiding exactly that choice. But if you force the choice, here is what you get. Either locality is false, meaning distant events can instantaneously influence each other, or realism is false, meaning particles genuinely do not have properties until measured. Or both are false. There is no option where both are true. The Copenhagen interpretation gives up realism. Particles do not have definite properties. Measurement creates reality. This is the standard choice, and it is the one most textbooks present as if it were the only option. The many worlds interpretation gives up neither, technically, but pays for it with an infinite number of unobservable parallel universes. Every measurement branches the universe. All outcomes happen. You just experience one branch. Locality is preserved because there is no collapse, no single outcome, and therefore no non-local influence. But you have to accept that right now there are infinitely many copies of you, living in infinitely many branches of configuration space, and you can never interact with any of them. The theory is local at the cost of being unimaginably profligate with reality. Pilot wave theory gives up locality, explicitly, proudly. The particles are real, they have definite positions at all times. Realism is preserved, but the guiding equation is non-local. The velocity of every particle depends on the positions of all other particles instantaneously, across any distance. And Bell's theorem says this is not optional. Any theory that keeps realism and reproduces the predictions of quantum mechanics must be non-local. Pilot wave theory does not hide from this. It puts the non-locality in the equation and lets you stare at it. And that is the choice the physics establishment has been running from since 1927. Not because non-locality is mathematically problematic. It is not. The theory works. Not because non-locality contradicts experiment. It does not. Every experiment ever performed is consistent with Bohmian mechanics. The establishment ran from it because non-locality is philosophically terrifying. It means the universe is not made of separate parts. It means what happens here is physically connected to what happens on the other side of the cosmos. It means the feeling you have that you are a separate entity, isolated in space, acting independently, is an artifact of not being able to see the wave function. If you could see it, you would see that every particle in your body is connected to every other particle in the universe through the guiding equation, with no diminishment, no weakening, no respect for distance. Bohm understood this better than anyone. In the 1980s, working at Birkbeck College with Basil Hiley, his closest collaborator, Bohm developed the philosophical framework he called the implicate order. The idea is rooted directly in the mathematics of configuration space. In a classical universe, you can describe the state of the system by listing the positions of all the particles in three-dimensional space. The particles are the fundamental objects, space is the arena, and locality is the rule. In a Bohmian universe, the wave function in configuration space is the more fundamental object. The particles in three-dimensional space are guided by it, shaped by it, moved by it. The three-dimensional world you experience is, in Bohm's language, the explicate order. It is the unfolded surface of something deeper. The implicate order is the wave function itself, the object in configuration space where everything is enfolded into everything else, where the separation between this and that, here and there, you and the distant galaxy, is not fundamental, but emergent. Bohm was very specific about this. He was not being mystical. He was doing physics. In his 1993 book, The Undivided Universe, written with Hiley and published posthumously 1 year after Bohm's death, the mathematics is laid out in rigorous detail. The quantum potential is derived, its non-local properties are proven. The connection between the guiding equation and the implicate order is formalized, and the implications are stated plainly. The quantum potential can be said to carry information about the whole environment and about the whole experimental arrangement, and to respond to this in a way that does not necessarily fall off with distance. That is not Bohm being a mystic. That is Bohm reading his own equation and telling you what it says. And notice what has happened to the word information in that sentence. In standard physics, information is something humans extract from measurements. It is epistemic. It lives in our models. In Bohm's framework, information is ontological. The quantum potential carries information. The wave function encodes information. not as a metaphor, as a physical process. The wave function informs the particles, telling them where to go, and it does so using the entire configuration of the universe as its input. Hiley took this further than Bohm had time to. After Bohm's death, Hiley spent 3 decades at Birkbeck developing what he called the algebra of process, a mathematical framework built on non-commutative geometry and Clifford algebras that treats process, rather than substance, as the fundamental category of physics. In Hiley's framework, the distinction between the implicate and explicate orders is not a philosophical gloss on Bohm's mechanics. It is a mathematical structure. The implicate order corresponds to the non-commutative algebraic level, where the usual notions of position and momentum do not commute and cannot be simultaneously defined. The explicate order corresponds to the commutative shadow, the classical limit, where separate objects in space appear to exist independently. Hiley continued this work for over 30 years after Bohm's death, right up until his own passing on January 25, 2025, at the age of 89. 3 of the 4 founders of the modern Bohmian program, Bohm, Bell, and Hiley, are now gone. Dewar died in 2000. Of the founding generation, only Goldstein and Zangi remain active. Whether Hiley was right that the implicate order points towards something beyond quantum mechanics remains to be seen. But here is what is not in doubt. The quantum potential is non-local. The guiding equation couples every particle to every other particle. Bell's theorem proves that any theory reproducing quantum predictions must have this feature. And these are not speculations. They are theorems. They are mathematical facts about the structure of quantum mechanics, proven in 1964 and experimentally confirmed beyond any reasonable doubt by 2015. But the implications go further than non-locality, and this is where Anthony Valentini's work at Imperial College London enters the picture, and where the story reaches its most unsettling depth. Valentini has been working on pilot wave theory since the early 1990s. His doctoral thesis, completed under Denis Sayama at the International School for Advanced Studies in Trieste, asked a question that nobody in the Bohmian mechanics community had taken seriously before. The question was this: in standard Bohmian mechanics, the statistical distribution of particle positions is assumed to match the Bohm rule. The probability of finding a particle in some region of space is given by the square of the wave function in that region. This is called quantum equilibrium. It is the state in which the predictions of Bohmian mechanics are identical to the predictions of standard quantum mechanics, and for all practical purposes, the universe appears to be in quantum equilibrium. Every experiment we have ever performed is consistent with the Bohm rule. But Valentini asked a question that seems simple and turns out to be devastating. Why? Why should the universe be in quantum equilibrium? In classical statistical mechanics, there is an analogous situation. The Maxwell-Boltzmann distribution describes the statistical distribution of molecular speeds in a gas at thermal equilibrium. But no physicist thinks the Maxwell-Boltzmann distribution is a fundamental law. It is an equilibrium condition. It arises because the gas has had time to relax, to mix, to explore its available states. If you start a gas in a non-equilibrium configuration, with all the fast molecules on one side and all the slow molecules on the other, it will evolve toward the Maxwell-Boltzmann distribution over time. The equilibrium is a consequence of dynamics, not an axiom. Valentini proposed that the Bohm rule is the same kind of thing, not a fundamental law, an equilibrium condition. The universe started in some initial state. The particles had some initial distribution of positions. Over time, through the dynamics of the guiding equation acting on the wave function, that distribution relaxed toward quantum equilibrium. The Bohm rule is not why reality works this way. The Bohm rule is what reality settled into after 13.8 billion years of dynamical evolution. This might sound like a philosophical distinction without practical consequences. It is not. Because if the Bohm rule is an equilibrium condition rather than a fundamental law, then there are two immediate and radical implications. The first implication is about the past. If the Bohm rule is an equilibrium condition, then there was an error before equilibrium was reached. An error in the very early universe, possibly in the first fractions of a second after the Big Bang, when the distribution of particle positions did not match the Bohm rule, when quantum non-equilibrium prevailed, and in a state of quantum non-equilibrium, the predictions of Bohmian mechanics diverge from standard quantum mechanics. The two theories are no longer experimentally equivalent. They give different numbers, different probabilities, different statistics. Valentini has calculated what those differences might look like. In a series of papers published between 2001 and 2000, he and his collaborators have shown that primordial quantum non-equilibrium would leave specific, potentially detectable signatures. The most promising place to look is the cosmic microwave background radiation, the afterglow of the Big Bang that was released approximately 380,000 years after the Big Bang, when the universe cooled enough for hydrogen atoms to form and light to travel freely. The CMB has been mapped with extraordinary precision, first by the COBE satellite in the early 1990s, then by WMAP from 2001 to 2010, and most recently by the Planck satellite, whose final data release came in 2018. These maps show the temperature of the early universe in every direction, and the fluctuations follow a very specific statistical pattern predicted by the standard cosmological model, except that they do not entirely. At the largest angular scales, the CMB contains anomalies that have troubled cosmologists for over 2 decades. The quadrupole, the largest scale pattern in the temperature map, is anomalously weak with a measured power roughly 7 times lower than expected. The quadrupole and octupole modes are aligned with each other in a way that standard inflationary cosmology says should be extraordinarily unlikely. There is a hemispherical power asymmetry, with one half of the sky showing systematically stronger fluctuations than the other. And there is the cold spot, a region in the southern galactic sky, roughly 10 degrees across. That is significantly colder than the standard model predicts, first identified in the WMAP data in 2004 and confirmed by Planck. These anomalies are statistically significant. They are not noise, but they have no accepted explanation within standard cosmology. They have been called curiosities, flukes, residual foreground contamination, or systematic errors. Valentini's proposal is that they might be none of those things. They might be fossils, remnants of an era when the Bohm rule had not yet established itself, when the distribution of primordial fluctuations was shaped by quantum non-equilibrium, producing correlations at the largest scales that standard quantum mechanics cannot account for, when the universe was still settling into the quantum equilibrium that we now take for granted. This is published research. It is not speculation. Valentini laid out the framework in his 2001 paper in Physics Letters A, volume 280, pages 1 through 8. He and his student Samuel Collin extended it in 2014 and 2016. His 2025 book, Beyond the Quantum, published by Oxford University Press, presents the full program. The mathematics is rigorous, the predictions are specific, and they are, in principle, testable with future CMB observations and with experiments probing the quantum statistics of primordial particles. The second implication is about what quantum non-equilibrium would mean if it still existed somewhere, and this is where the theory crosses a line that most physicists do not want to approach. In quantum equilibrium, the non-local connections in the guiding equation are real but unexploitable. You cannot use entanglement to send a message faster than light, because the statistical randomness of measurement outcomes, which arises from your ignorance of the exact particle positions, screens off any attempt to encode information. This is the no-signaling theorem, and it is one of the pillars of modern physics. It is what allows quantum mechanics and special relativity to coexist peacefully. But the no-signaling theorem depends on the Bohm rule. It assumes quantum equilibrium. Valentini proved in his 1991 thesis and subsequent publications that in a state of quantum non-equilibrium, the no-signaling theorem breaks down. If the distribution of particle positions deviates from the Bohm rule, then the non-local connections in the guiding equation can be used to transmit information faster than light, instantaneously, across any distance. Read that again. If quantum non-equilibrium exists anywhere in the universe, anywhere at all, then faster-than-light communication is not just possible in principle. It is a consequence of the fundamental dynamics the guiding equation permits it. The only thing preventing it is the Bohm rule. And the Bohm rule in Valentini's framework is not a law, it is a contingent fact about the current state of the universe, a state that might not hold everywhere, a state that did not hold in the early universe, a state that might be artificially disrupted if you knew how to push a quantum system out of equilibrium without it relaxing back. The mechanism is specific. In quantum equilibrium, if Alice and Bob share an entangled pair of particles, and Alice measures her particle, the distribution of Bob's outcomes is statistically independent of what Alice chose to measure. Bob cannot tell what Alice did. The non-local connection is real, but it is statistically invisible, masked by the equilibrium distribution. This is why you cannot use entanglement to send a message in standard quantum mechanics. The correlations only become visible when Alice and Bob compare their results later through a classical communication channel that respects the speed of light. But in quantum non-equilibrium, the particle positions are not distributed according to the Bohm rule. The statistical masking fails. Bob's measurement outcomes become systematically dependent on Alice's measurement choice. He can read the message, the non-local connection, which was always there in the guiding equation, becomes visible, exploitable, and usable for communication. And there is no limit on the distance. The quantum potential does not diminish. The signal does not degrade with spatial separation. If Alice is on Earth and Bob is on a planet orbiting a star in the Virgo cluster, 50 million light-years away, the signaling works exactly the same as if they were in adjacent rooms, instantaneously, without any intermediary, without anything traveling through the space between them. Valentini is explicit about the stakes. In a 2002 paper titled Signal Locality in Hidden Variables Theories, published in Physics Letters A, volume 297, pages 273 through 278. He wrote that subquantum non-equilibrium would represent a new and more powerful kind of non-locality that could be used for practical superluminal signaling. He has also argued, in subsequent papers and in his 2025 book, that a civilization with access to quantum non-equilibrium would possess capabilities so far beyond our current technology that we would not recognize them as technology at all. They could communicate instantaneously across galactic distances. They could influence distant systems without sending anything through the intervening space. They would, from our perspective, appear to violate the laws of physics, because the laws we know are equilibrium laws, and they would be operating outside equilibrium. The reason this is not front-page news is the same reason Bohr's papers were not front-page news in 1952. The implications are too large. The professional culture is too entrenched, and the default response to implications that are too large is not engagement, it is silence. This is not fringe physics. Valentini is a faculty member at Imperial College London, one of the most respected physics departments on Earth. His work has been cited hundreds of times. It has been presented at major conferences including the Solvay conference itself, the same conference where de Broglie's theory was silenced in 1927. The irony of that is almost too precise to be accidental, but the physics establishment, by and large, has treated Valentini's program the same way it treated Bohm's papers in 1952, not with refutation, with silence. The work is published. The mathematics is correct. The predictions are specific, and the response from most of the profession has been to look the other way. Ask yourself why. Ask yourself what it means that a mathematically rigorous, peer-reviewed research program published in top journals and presented at top conferences, proposing that the most fundamental statistical law in quantum mechanics might be an equilibrium condition rather than an axiom, and that its violation would enable faster-than-light communication, is met with the same institutional silence that greeted Bohm's papers 70 years ago. The pattern has not changed. The mechanism has not changed. The reason has not changed. The physics community does not ignore these ideas because they are wrong. It ignores them because the implications are too large, too strange, too threatening to the conceptual framework that everyone was trained in. And now you need to consider what all of this means together. Because up to this point, you might have been thinking about pilot wave theory as an intellectual curiosity, an alternative interpretation, an interesting philosophical position, something to argue about at conferences and in the comment sections of physics videos. And at that level, it is academically interesting but emotionally manageable. You can hold it at arm's length. You can treat it as one option among several, the way that 2025 Nature Survey frames it. But here is the thing that should make it unmanageable. Everything I have described is not a collection of disconnected claims. It is a single coherent picture of reality. And if that picture is correct, even possibly correct, then you need to sit with what it actually says about you, right now, in this moment. Start with the particles. Every atom in your body is made of particles. Electrons, protons, neutrons, quarks. In pilot wave theory, every one of those particles has a definite position at every moment. There is no uncertainty about where they are. The uncertainty principle, in Bohmian mechanics, is not a statement about reality. It is a statement about what you can know. The particles have positions. You just cannot measure them precisely because the act of measurement disturbs the guiding wave in a way that limits your information. The fuzziness is epistemic, a limit on your knowledge. It is not ontological. It is not a limit on what exists. Now add the guiding equation. Every one of those particles is moving along a trajectory determined by the wave function. The velocity of each particle at each moment is a precise mathematical function of the wave function evaluated at the actual positions of all the particles, not the nearby particles. All of them. The electron in your prefrontal cortex is being guided by a wave that depends on the positions of electrons in the Andromeda galaxy. The connection does not weaken, the quantum potential does not diminish. Distance is irrelevant to the guiding equation. Now add determinism. The Schrödinger equation is deterministic. Given the wave function at one time, you can calculate the wave function at any future time with perfect precision. Given the wave function and the particle positions at one time, the positions at all future times are uniquely determined. There are no dice being rolled. There are no random choices being made. The evolution of the entire system, wave function plus particle positions, is as determined as the orbit of a planet. More determined, in fact, because planetary orbits are chaotic, sensitive to initial conditions in a way that makes long-term prediction impossible in practice. The guiding equation is also sensitive to initial conditions, but the dynamics are exact. In principle, with perfect knowledge of the initial conditions, every future configuration of every particle in the universe is calculable. And the initial conditions were set at the Big Bang, approximately 13.8 billion years ago. Whatever the state of the wave function was at that moment, whatever the positions of all the particles were at that moment, the subsequent evolution was determined. Every trajectory, every configuration, every atom that would eventually form a star, a planet, a molecule, a cell, A neuron. Every electrochemical signal that would fire in every brain that would ever exist. All of it encoded in the initial conditions and unfolded by the guiding equation over 13.8 billion years. That includes you. That includes the neurons firing in your brain right now. That includes the sensation you are experiencing of choosing to keep listening, or choosing to stop, or choosing to dismiss what you are hearing. In a Bohmian universe, those choices are not choices. They are trajectories. They were determined by the initial conditions of the universe, propagated forward through the guiding equation, and they could not have been otherwise. The feeling of agency, the experience of deciding, is real as an experience. It is a feature of what it is like to be a particular configuration of particles being guided by a wave you cannot see. But it is not what you think it is. It is not free will. It is the guiding equation doing what it has always done, moving particles along paths that were fixed before the Earth existed. Now, you might object. You might say that determinism is not unique to pilot wave theory. Classical Newtonian mechanics was deterministic. The orbits of the planets are determined by initial conditions, and nobody thinks planetary orbits threaten free will. The difference is that Newtonian mechanics was replaced by quantum mechanics, which appeared to restore genuine randomness to the universe. The Copenhagen interpretation explicitly says that measurement outcomes are fundamentally random, not determined by hidden causes, not predictable even in principle, just random. And that apparent randomness has been used for nearly a century as an escape hatch from determinism. People say the universe is not deterministic because quantum mechanics is random, therefore free will is not threatened. Pilot wave theory closes that escape hatch. It says the randomness was never real. It was always ignorance. The particles always had positions. The trajectories were always determined, and the quantum uncertainty that was supposed to make the universe safe for free will was a feature of an equilibrium distribution, not a feature of fundamental physics. If pilot wave theory is correct, there is no randomness anywhere in the universe. There never was. And the century of comfort that physicists and philosophers drew from quantum indeterminacy was based on a philosophical choice made in a conference room in Brussels, not on an established fact about nature. Sit with that for a moment. Really sit with it. The entire cultural apparatus that humans have built around quantum mechanics, the pop science interpretations, the self-help books about quantum consciousness, the vague reassurances that the universe is open and creative and full of possibility, at the fundamental level, all of it depends on one assumption, that quantum randomness is real, that when a radioactive atom decays or a photon passes through a beam splitter, or a neurotransmitter is released at a synapse, there is a genuinely undetermined moment when nature rolls its dice, and the outcome could have been different. That assumption is the foundation of every argument that quantum mechanics rescues free will from the clockwork determinism of classical physics. And that assumption is a choice, not a fact, a philosophical choice made by a specific group of physicists at a specific historical moment, for reasons that had more to do with social dynamics than with mathematics. De Broglie had the deterministic version in 1927. Bohm had the complete deterministic version in 1952. Both reproduce every quantum prediction. Both say the dice were never rolled. And the only reason you grew up believing in quantum randomness is that the deterministic alternative was suppressed. If you find determinism disturbing, good, you should. Because the determinism in pilot wave theory is not the distant abstract determinism of Newtonian mechanics, where you can comfort yourself with the thought that predicting a human brain is practically impossible, even if theoretically determined. The determinism here is backed by non-locality. The trajectory of every particle in your brain is determined not just by local conditions, but by the positions of every particle in the universe, through a wave function that connects everything instantly. The computation that determines your next thought is not happening inside your skull. It is happening everywhere. The whole universe is the computer, and you are one subroutine. You can reject pilot wave theory. Many physicists do, but you cannot reject it on experimental grounds. Every experiment that confirms standard quantum mechanics also confirms Bohmian mechanics. The two are empirically equivalent, at least in the regime of quantum equilibrium. You can only reject it on philosophical grounds, because you do not like determinism, or because you do not like nonlocality, or because you find the wave function living in configuration space distasteful. Those are legitimate aesthetic objections. They are not scientific refutations. And the people who suppressed this theory for 60 years, who ignored it, who mocked it, who called it juvenile and metaphysical and foolish, never had a scientific objections. And they enforced those aesthetic objections with the full weight of professional and institutional power. Sheldon Goldstein, professor of mathematics at Rutgers University and one of the three architects of modern Bohmian mechanics, alongside the late Detlef Dürr and Nino Zanghi, has been writing about this for decades. In a 2009 paper titled Bohmian Mechanics and Quantum Information, Goldstein and his colleagues demonstrated that Bohmian mechanics not only reproduces quantum predictions, but provides a clearer foundation for quantum computing and quantum information theory than the standard formalism. The particles always have positions. The wave function always evolves unitarily. There is no mysterious collapse. The clarity of the ontology, Goldstein argues, is not a bug. It is the entire point. Dürr, Goldstein, and Zanghi published their foundational paper on quantum equilibrium in 1992 in the Journal of Statistical Physics, volume 67, pages 843 through 907. They showed that if you assume a typical initial condition for the universe, meaning an initial particle configuration that is not specially contrived, then the Bohm rule emerges naturally from the dynamics of the guiding equation. The Bohm rule does not need to be postulated. It is a consequence of the theory, the same way thermal equilibrium is a consequence of classical statistical mechanics. The randomness you observe when you measure a quantum system is real as a practical matter, but it is not fundamental. It is the noise of a deterministic system too complex for you to track. This is the framework. Particles with definite positions, guided by a wave function that lives in configuration space and connects everything to everything else. Deterministic evolution from initial conditions set at the Big Bang. Randomness emerging from ignorance, not from nature. Non-locality that is not hidden or implied, but written into the fundamental equation of motion. A measurement problem that does not exist because particles always have positions and measurement devices always have definite outcomes. And notice what this framework does not need. It does not need an observer. It does not need a measurement postulate. It does not need to define the boundary between the quantum world and the classical world, because there is no boundary. The same laws apply everywhere, at every scale, from electrons to planets to galaxies. The Schrödinger equation governs the wave function. The guiding equation governs the particles. That is the entire theory. Two equations, no exceptions, no, and then a miracle occurs at the moment of measurement. Compare that to the Copenhagen interpretation, which needs the Schrödinger equation plus a collapse postulate that no one can define precisely, plus a measurement axiom that no one can formalize, plus a division between quantum and classical regimes that no one can locate. Or compare it to many worlds, which needs the Schrödinger equation plus an infinite number of unobservable branches of reality, plus a derivation of the Bohm rule from the branching structure that has been attempted for decades and remains controversial. Pilot wave theory is simpler. It has more moving parts in one sense, the particle positions in addition to the wave function, but fewer ad hoc additions. It is the only interpretation that tells a complete physical story from start to finish without invoking anything mysterious, undefined, or unobservable. The fact that this is the interpretation with 7% support tells you everything you need to know about how physics as a profession handles uncomfortable truths. And the only reason this framework is not the standard way quantum mechanics is taught is that in 1927, a young physicist was pressured into abandoning his correct theory. In 1952, an exiled physicist published the completed version and was answered with organized silence. In 1964, a self-taught physicist at CERN proved the nonlocality was inescapable and published it in a journal nobody read. And for the next 60 years, the professional culture of physics declared that asking what the theory means was unprofessional. The pattern has not changed. The 2025 Nature survey shows no interpretation commands majority support. Only 24% of researchers are confident in their choice. The foundations of quantum mechanics remain unsettled after 100 years. And the theory that solves the measurement problem, that eliminates the paradoxes, that gives you a clear physical picture of what is happening, is supported by 7%. After a century. Think about what that means. Not for physics, for you. There is a community of researchers, small but dedicated, who are pushing this forward. And the biographical details of these people matter, because they tell you something about the kind of person who chooses to work on a marginalized theory in a profession that punishes dissent. Sheldon Goldstein has been a professor of mathematics at Rutgers University since 1977. He did not come to Bohmian mechanics from physics. He came from probability theory and mathematical physics. In the late 1980s, he connected with Detlef Dürr in Munich and Nino Zanghi in Genoa, and the three of them began building the modern mathematical framework for Bohmian mechanics from the ground up. Their collaboration lasted over 30 years. They published dozens of papers together. They trained students. They organized workshops. They did this work knowing that it would not lead to the kind of recognition that mainstream quantum information or string theory research attracts. They did it because the mathematics was right and the physics was clear, and somebody had to do it. Dürr died on January 3rd, 2021, at the age of 69. He was a professor at Ludwig Maximilian University in Munich. He had spent decades teaching students how to think carefully about the foundations of quantum mechanics in a department and a country where foundations work was slightly less stigmatized than in the United States, but still far from fashionable. His textbook, Bohmian Mechanics, written with Stefan Teufel and published in 2009, remains the most rigorous introduction to the subject. Roderick Tomulka, now at the University of Tübingen, was one of Dürr's doctoral students. He has done more than almost anyone to address the relativistic extension problem, the main technical challenge facing Bohmian mechanics. His work on what he calls flash ontology, a version of Bohmian mechanics where the fundamental objects are not persistent particles but discrete events in space-time, offers one possible route to a relativistic theory. In a 2006 paper in the Journal of Statistical Physics, volume 126, pages 126-9 through 1107, Tomulka constructed an explicitly relativistic model for non-interacting fermions that is fully Lorentz covariant in its predictions, while retaining the Bohmian structure underneath. The model has a preferred foliation, but that foliation is empirically undetectable. The universe looks relativistic from the outside while being non-local underneath. Travis Norson at Smith College in Massachusetts has written what many consider the best pedagogical treatment of Bell's theorem and its implications. His 2017 book, Foundations of Quantum Mechanics, is one of the few textbooks that gives Bohmian mechanics a full, fair, and rigorous presentation, alongside Copenhagen and Many Worlds. Norson has been particularly effective at clearing up misconceptions about Bell's theorem. showing that it does not merely rule out local hidden variables in some narrow technical sense, but places deep constraints on the structure of any theory that reproduces quantum correlations. Ward Struve at KU Leuven in Belgium works on Bohmian field theory, the extension of particle-based Bohmian mechanics, to quantum field theories where particle number is not conserved. This is one of the frontiers of current research. In standard quantum field theory, particles are created and destroyed. How does a pilot wave theory handle a system where the number of things being guided by the wave changes? Struve and others have proposed several approaches, including field ontologies, where what is guided is not particles, but field configurations. The work is ongoing. The problem is hard, but it is a specific, well-defined mathematical problem which is more than can be said for the interpretive difficulties plaguing competing frameworks. And Valentini at Imperial College London, whose non-equilibrium program we have already discussed. Valentini's career is itself a case study in what happens to researchers who take pilot wave theory seriously in the current professional climate. Despite a position at one of the world's premier physics departments, despite publication in top journals, despite a research program with specific testable predictions, Valentini's work remains outside the mainstream conversation about quantum foundations. It is cited respectfully by those who engage with it. It is simply not engaged with by most of the field. The annual conferences continue. The Tauler Institute workshops in Tuscany, organized in the hills outside Florence, bring together a few dozen researchers each year to work intensively on open problems in Bohmian mechanics. The Emergent Quantum Mechanics series holds meetings in Vienna and beyond. The Oxford Centennial volume on guiding waves, published in 2025 to mark 100 years since de Broglie's thesis, collected contributions from researchers across the Bohmian community and was published by a major academic press. Adam Kay's 2024 book Escape from Shadow Physics, published by Basic Books, brought the suppression story to a general audience for the first time in decades. They are not a fringe, they are the resistance to a consensus that was never earned by evidence. And the theory has an open wound: the relativistic problem. Bohmian mechanics, as formulated by Bohm in 1952, is a non-relativistic theory. It reproduces non-relativistic quantum field theory, the framework that describes particle creation and annihilation, antimatter, the behavior of fields at high energies, and the marriage of quantum mechanics with Einstein's special relativity, remains an unsolved problem. The non-locality in the guiding equation seems to require a preferred foliation of space-time, a special slicing of the four-dimensional space-time continuum into three-dimensional snapshots, ordered in time. This preferred foliation provides the simultaneity structure needed for the instantaneous non-local influences in the guiding equation to be well defined. Without it, the word instantaneous has no meaning, because in special relativity, what counts as the same time depends on how fast you are moving. But special relativity says there is no preferred foliation. There is no absolute simultaneity. Different observers moving at different speeds slice space-time differently, and no slicing is privileged. This was the heart of Einstein's 1905 revolution. It was the insight that time is not absolute, that simultaneity is relative, that there is no cosmic now that applies everywhere. And pilot wave theory seems to need exactly the thing Einstein said does not exist. This tension is real and it is unresolved, but it is more subtle than it first appears. Dürr, Goldstein, Tumulka, and Zangi have shown that you can construct a Bohmian theory with a preferred foliation that is empirically indistinguishable from standard relativistic quantum mechanics. The foliation is there in the mathematics, but it is hidden from observation. No experiment can detect it. No measurement can reveal which foliation is the real one. The theory predicts exactly the same observations as standard relativistic quantum mechanics, including all the Lorentz invariant predictions that are the hallmark of special relativity. The foliation is like a hidden scaffolding. It supports the non-local dynamics but leaves no visible trace. In a 2014 paper in the Journal of Physics A, Volume 47, Article 116002, Tumolka presented a relativistic Bohmian model for non-interacting fermions that is fully Lorentz invariant at the level of predictions, despite having a preferred foliation in the background. The model is mathematically rigorous. It reproduces all the predictions of the standard Dirac equation, and it does so with particles that have definite positions at all times, and trajectories that are guided by a wave function through a mechanism that is explicitly non-local. For the full interacting theory, relativistic Bohmian quantum field theory with realistic interactions between particles, where particles can be created and destroyed and field configurations can change, has not been completed. Several approaches exist. Some use field ontologies, where what the wave function guides is not particles but field values at every point in space. Some use particle ontologies with variable particle number, where the guiding equation is supplemented with rules for particle creation and annihilation. Some, like Tumolka's flash ontology, replace persistent particles entirely with discrete space-time events. None of these has yet achieved the status of a complete, universally accepted relativistic Bohmian theory. This is the edge that Bohm felt he was on when he died, the edge that Hiley worked on until January of 2025, the edge that Dürr worked on until his death in January of 2021. It is the unfinished problem, the place where the theory reaches toward a complete description of reality and has not yet grasped it. Does that open wound invalidate the theory? The Copenhagen interpretation does not have a relativistic measurement theory either. Nobody has explained how wave function collapse, which is supposed to be instantaneous, is compatible with special relativity. The many worlds interpretation has its own unresolved problems, including the probability problem, the fact that the branching structure of the wave function does not obviously yield the Born rule, despite decades of attempts to derive it. Every interpretation of quantum mechanics has open problems. Pilot wave theory's open problem is at least a specific, well-defined mathematical question. Can you extend the Bohmian dynamics to relativistic quantum field theory in a way that is fully consistent? The other interpretation's open problems are more fundamental. What is measurement? What is collapse? How do probabilities work in a deterministic branching multiverse? But the open wound matters for a different reason. It means the story is not finished. The deepest implications of pilot wave theory have not been fully mapped. The connection between the deterministic non-local Bohmian picture and the relativistic structure of space-time has not been resolved. And until it is resolved, there remains the possibility that the resolution will reveal something even more disturbing than what we already know. That the preferred foliation is real and detectable, which would mean there is a privileged frame of reference in the universe. That quantum non-equilibrium exists in pockets of the cosmos, which would mean faster than light signaling is not just theoretically possible but occurring somewhere right now. That the wave function in configuration space is not the deepest level of description, and the Bohm's implicate order points to a structure beneath quantum mechanics that we have not yet discovered. Bohm sensed this. He spent his last decades talking about it, writing about it, frustrating his colleagues who wanted him to stay within the boundaries of conventional physics. He told the physicist F. David Peat in interviews collected in the book Science, Order and Creativity that he believed physics was stuck in a rut because it refused to consider the possibility that the mathematical structures it used were approximations to something deeper. He was not abandoning rigor. He was insisting on a kind of rigor that the profession did not reward. The rigor of asking what the equations mean. The equations mean this: the universe is one system, not a collection of parts. One system. The wave function is one object, defined on one space encoding the relationships between every particle simulationally. The particles move along trajectories that are determined by the wave function and by the positions of all other particles, instantaneously, non-locally, with no respect for distance. The trajectories are deterministic. The initial conditions, set at the origin of the universe, determined everything that follows. The apparent randomness of quantum mechanics is ignorance masquerading as ontology. The apparent separateness of objects in space is an artifact of living in 3 dimensions when the physics is happening in 10 to the 80 times 3, and you are part of it. Not as an observer, not as a measurer, not as a special entity that collapses wave functions by looking at things. You are part of the system. Your particles have positions. Your trajectories are determined. The wave function that guides the electron in a distant quasar is the same wave function that guides the electrons in your visual cortex as you process these words. There is one wave function, there is one guiding equation, and there is one set of initial conditions from which everything follows. Consider what that means concretely. The sodium and potassium ions flowing through the ion channels in your neurons right now, the ones creating the electrical signals that your brain interprets as thoughts. Each of those ions has a definite position. Each one is being guided by the universal wave function, the timing of each ion channel opening, the strength of each synaptic signal, the cascade of neurotransmitter release that constitutes the physical substrate of what you experience as thinking. All of it is governed by the guiding equation. All of it depends, through the quantum potential, on the configuration of every other particle in the universe, and all of it was determined by the initial conditions. The thought you are having right now, about whether to believe this, about whether determinism is really as unsettling as the script is claiming, about whether there is some escape, some way out, some reason this does not apply to you, that thought is itself a product of the guiding equation. Your skepticism was determined. Your doubt was determined. Your decision about what to do after this video ends was determined, not by anything inside your skull alone, by everything. By the wave function of the universe, evolving since the Big Bang, shaping the trajectories of 10 to the 80 particles according to a law that has no randomness in it anywhere. And the vertiginous part is not the determinism itself. Plenty of philosophies have grappled with determinism. The vertiginous part is the non-locality. In a classical deterministic universe, you could at least say that your thoughts are determined by local conditions, by the atoms in your brain, the photons hitting your eyes, the sound waves entering your ears, local causation, nearby causes producing nearby effects. You are a machine, perhaps, but at least you are a self-contained machine. In a Bohmian universe, you are not self-contained. The quantum potential that guides the particles in your brain depends on particles everywhere. The electron in a hydrogen cloud in the Carina Nebula, 7,500 light-years away, is as present in the equation governing your neural activity as the electron in the neuron next to it. Your thoughts are not locally produced, they are globally produced by a wave function that encompasses everything, connects everything, and has been evolving everything in lockstep since the beginning. You were not told this because in 1927, a room full of the most brilliant people who ever lived decided they would rather not think about it. They chose randomness over determinism. They chose vagueness over clarity. They chose the comfort of not knowing over the discomfort of what knowledge would require. And then they built a professional culture that enforced that choice for a century, destroying careers, burying papers, and teaching generations of physicists that the most fundamental question in their field was not worth asking. De Broglie knew the answer in 1927 and was pressured into silence. He spent 25 years following an interpretation he did not believe before finding the courage to return to his own work. He died in 1987 at 94, having outlived both Bohm and Bell, having watched the theory he birthed get suppressed, revived, suppressed again, and slowly, painfully begin to resurface. Bohm knew the answer in 1952 and was exiled for it. Not for the physics, for refusing to betray his colleagues to a congressional committee. He spent 40 years in exile, published some of the most important papers in the history of quantum mechanics from a succession of foreign institutions, and died in a taxi on a London evening in 1992, feeling he was on the edge of something he did not live to reach. Bell knew the answer in 1964 and was forced to pursue it as a hobby. The most important theorem in quantum physics was proved by a man who could not work on it professionally. He died of a cerebral hemorrhage in 1990, at 62, 12 years before the Nobel Committee acknowledged that his work mattered, and 32 years before the experiments that confirmed it beyond all doubt. 3 men, 3 lifetimes. Each one saw the answer clearly, and each one paid for seeing it. Not because they were wrong, because they were right at the wrong time, in the wrong field, in a profession that had decided the question was not worth asking. The question is worth asking. It has always been worth asking, and the answer has been sitting in the literature since 1952, written by a man in exile, reviewed and found correct by every serious critic. Demonstrated on a tabletop in Paris, proved inescapable by a theorem from Belfast, and ignored by a profession that could not face what it implies. The wave function is real. The particles have positions. The trajectories are determined. The universe is non-local, and the wave that guides every particle in existence, including every particle in you, has known where you would be since before the stars formed. Not because it is watching you, not because it cares, because the guiding equation is a law of nature, and laws of nature do not have opinions. They simply run, from initial conditions through 13.8 billion years to this moment, to you hearing this, to the neurons firing in the pattern they were always going to fire in, to the thought forming in your mind right now, the one that feels like yours, that feels like a choice, that feels like you deciding what to think about everything you have just heard. That thought was in the initial conditions. The wave has always known it, and you were never supposed to find out.